Hello friends. So, we saw in our previous lecture how the terms for polynomial approximation within finite elements in 2 dimension are chosen to be symmetrically placed in Pascal triangle. So, the whole idea about symmetric placement in Pascal triangle is to maintain the balance between coordinate directions, so that the element formulation becomes independent of the choice of frame of reference, and then the user may choose whatever frame of reference that might be convenient for the problem at hand. The results are not going to be sensitive to the choice of frame of reference. So, it is very important that the required terms in polynomial approximation should be chosen so as to be located symmetrically about the center line and as close to the center line as possible if there are multiple possibilities. So, now we take our discussion further and get to the actual implementation design of finite elements of 2 dimension, and we will start with triangular elements, family of triangular elements. As we discussed, triangle is the simplest 2 dimensional figure which can enclose an area. So, the whole idea is we need to represent the domain by a patchwork of triangles, patchwork of finite elements which will cover the entire domain, and we construct approximation over individual element, and the simplest element that can cover 2 dimensional domain is a triangle. So, let us start with triangular elements. So, the simplest element of this family is a 3 noded triangle, and we briefly saw this in our couple of lectures back. The simple element is defined by 3 vertices, and the field variation of primary variable within this 3 node triangle is given by the complete polynomial up to first degree with 3 independent terms, that is linear terms x, linear term in x, linear term in y, and a 0th order term. So, the constant term 0th degree polynomial. I can rearrange this, segregate the polynomial terms on one side and the coefficients on the other in the other factor. So, I can express this polynomial expansion as a product of polynomial terms and coefficients. So, this is what we refer to a 0, a 1, a 2, they are the coefficients, unknown coefficients of this polynomial, also known as generalized coordinates. So, the polynomial approximation can be represented as P A. P is the matrix of polynomial terms, in this case 1, x and y. So, P is a row vector of polynomial terms, A is a vector of polynomial coefficients known as generalized coordinates, and these are to be evaluated from the requirement of interpolation of this primary of the approximation of primary variable. So, interpolation model of primary approximation requires that when I evaluate this polynomial approximation at respective coordinates of the nodes, for example, coordinates of ith node are x I, y I. So, if I evaluate this approximation at x I, y I, I should get the value of the primary variable at ith node, that is u I, right, and similarly for u j and u k. So, jth node and kth node, or if we go by numeric identifiers. So, nodes 1, 2 and 3. So, once we do that, so the primary variables u 1, u 2, u 3 defined at 3 nodes 1, 2 and 3 defined by the coordinates x 1, y 1, x 2, y 2, x 3, y 3. So, together the variable, the interpolation model of this approximation requires that this condition should be satisfied. So, once we have this, so this matrix of coefficient, the matrix of coordinates of the nodes, that is invertible matrix as long as none of the 2 rows and columns are linearly dependent, and which is guaranteed if the 3 nodes of the triangle are not collinear, and which is obviously if it is a triangle, then obviously all 3 nodes cannot be collinear, and that way it will not be enclosing any area. So, if it is enclosing area, then there is no way this matrix can be singular, and therefore, it is invertible, and A can be solved in terms of u, and that is what we get. A is equal to C inverse u, and then we substitute this A solution for A in our previous approximation, that is u as a function of x and y is given as P A. So, we substitute for A here. So, we get P C inverse multiplied by u, nodal variables, nodal values of the primary variable, and then collecting these terms. So, this matrix P C inverse, I call this as n 1 as a function of x and y, second term n 2 as a function of x and y, third term n 3 as a function of x and y, multiplied by the vector of nodal values of the primary variable u, u1, u2, u3. So, these functions n1, n2, n3 are the desired interpolation functions for the corresponding nodes, and they satisfy, it can be verified that they satisfy the basic requirement of the interpolation function, that is n I when evaluated at x j y j is equal to delta I j, the Kronecker delta, which is equal to unity if I is equal to j, and it is equal to 0 if I is not equal to j, I and j being the nodes of interpolation. So, the nodes of the primary variable interpolation. Now, there is of course, this can be extended, and for first degree polynomial approximation, it is a very simple 3 by 3 matrix, and inverting a 3 by 3 matrix is not that much of an issue, can be done. It is a little tedious, but it can be managed. But if I do this for let us say quadratic element, if I want to have a higher degree of approximation. So, let us say quadratic. So, quadratic terms would require 6 nodes of interpolation, 6 nodes for interpolation, right. So, 3 vertices and 3 mid side nodes of the triangle. So, these together they will provide the 6 conditions for evaluating 6 known coefficients, because there would be 3 more terms corresponding to quadratic, x square, x y and y square, in addition to these 3 terms for complete up to first degree polynomial approximation. So, going through the same process by way of P C inverse, it is possible to do that, but it becomes increasingly more complicated. So, there has to be we can find out some other procedures which can be developed, which can be more easily adopted, and we will see how we can effortlessly generate interpolation functions for higher order interpolations even in for triangular elements. Now, in addition to that, we have another way of constructing these interpolation functions for the 3 noded triangle. We can just look at these coordinates, and that is enough to this C matrix. By inspection of C matrix, it is possible to derive the interpolation functions. Of course, after going through that, we can observe there are some cyclic symmetries that can be exploited in the terms, and that is what we do. So, shape functions may also be directly obtained from the nodal coordinates as an ith node shape function as a function of x and y is given as 1 over twice delta alpha I plus beta I x plus gamma I y. Now, alpha I is a coefficient. Now, you look at it, what is this coefficient? Alpha I is equal to x j y k minus x k y j. Now, if you look at it previous expression, alpha I is a constant term, it multiplies the constant. So, if I multiply this constant term, so I am looking at constant term. So, I remove first column and first row, that corresponds to the alpha I term, constant term, I am left with x j y k minus x k y j, and that is what this is, x j y k minus x k y j, right. And of course, there is a constant denominator, that is 2 delta. Delta is the area of the triangle, and the property of this matrix is, determinant of this matrix is equal to twice the area of the triangle defined by these 3 vertices, right. So, if I take the determinant of this coordinate matrix, that is equal to twice the area of the triangle. So, if delta is what I call as the area of the triangle, so 2 delta is same as the coordinate of determinant of matrix C. Now, beta I, similarly beta I is a multiplier of linear term x. So, I look at this beta I. So, beta I is equal to, it will be y 3 minus y 2 multiplied by, so that will be multiplied by minus 1, that is because it is taking the one corner off. So, y 2 minus y k, and similarly gamma j, gamma I will be corresponding to the yth term. So, yth term, so it is x 3 minus x 2 multiplied by minus 1 raised to the power what is it 1 plus 3 4, right. So, that way it is very simple to do that. So, x k minus x j, so or minus x j minus x k, and similarly if I do this I can similarly go back and work out what are the interpolation functions for n j and n k just by looking at that matrix of coordinates, or starting with these expressions I can just go for cyclic permutation. Wherever I have I replace it by j, wherever I have j I replace it by k, wherever I have k I replace it by I, then I will get the coefficients for shape functions j. And similarly, once having obtained shape functions, interpolation functions for node j, I can again go back, and wherever I have j I can replace it by k, wherever I have k I can replace it by I, and wherever I have I replace it by j. So, that way so essentially that is what the cyclic permutation is. I goes to j, j goes to k, and k goes to, wherever you have k it goes to I. So, this cyclic permutation, if we do this cyclic permutation, we can derive the interpolation functions for all the 3 nodes. So, that is another way of deriving these interpolation functions for 3 noded triangle. Now, polynomial approximation, as we see, it is complete up to the first degree constant term, first degree in x, first degree in y, and therefore, accordingly the approximation, if I write u hat as a function of x and y is equal to n 1 x y multiplied by u 1 plus n 2 x y multiplied by u 2 plus n 3 as a function of x y multiplied by u 3. Now, n 1 is a linear function in x and y, n 2 is also a linear function in x and y, n 3 is also a linear function in x and y, u 1, u 2, u 3 they are to be treated unknown constants, they are unknown constants. So, this expression total is a first degree polynomial. So, if this is a first degree polynomial, then what will be the partial derivative del u by del x and del u by del y, right. So, this is going to be a constant because there is only first degree term, the x appears only in the first power. So, first derivative is going to be constant and all other terms would vanish looking at the variation with respect to x, and similarly del u by del y is also going to be constant because there is only first degree term in y, right. So, the only variation available is with respect to first degree in y. So, the first derivative is going to be constant. So, both of them, so del u by del x and del u by del y, they are constants. So, we have this special name for this triangle, it is called constant strain triangle. It means throughout the domain, if I have this triangle, right, I, j and k. So, if I have this triangle, then irrespective of wherever I evaluate the derivative value, the derivative value will always be evaluated to be same. So, all through the element it is a constant derivative, or the strain in this element everywhere within the element is constant, and therefore, this is known as constant strain triangle. And this was the first finite element to have been developed and extensively studied and extensively used. So, this is also the requirement for monotonic convergence, because in the limit as the element size becomes 0, as I refine, I can refine this mesh, I can have 2 different elements, and then I can also have something like this. So, I can refine the element domain. So, now one domain is now covered by 1, 2, 3, 4, 5, 6, 6 elements, and each of these 6 elements they are smaller. So, as the elements finite element size becomes smaller and smaller, this is called mesh refinement, and this is like adding more and more number of terms to the series approximation. So, we have infinite series, we can keep on adding more and more number of terms, and the approximation of the series approximation becomes finer and finer. So, this is what is mesh refinement is similar to that. So, I can we can actually divide the domain into smaller and smaller by using smaller and smaller finite elements. Now, in the limit as the finite size of the finite element becomes very small, that at that one point the strain is obviously going to be a constant value. So, this essential feature of mechanics, that the derivative has to be constant at a point, and in the limit as the finite element approaches a point in the limit of discretization, then it should be able to represent that constant derivative condition, or in case of structural mechanics applications, it should be solid mechanics application, it should that corresponds to constant strain states, right. So, this is very important, and then the requirement of constant term itself in the approximation, that alpha I or a 0, that is also important, and that is required to generate capture the rigid body mode of deformation. For example, this, as we discussed earlier, if I move this body, there is no constraint, then it will move as a whole without any strain developing anywhere, and that rigid body movement is essential, otherwise it will it is not, we may get erroneous results. So, these two criteria, the rigid body motion and constant strain states, they are essential requirements for the convergence of finite element solution. And then having looked at these are the requirement within one element, that it has to have a constant strain state, it has to have capability to represent rigid body deformation, rigid body motion, not deformation. So, rigid body motion should be possible, but then the next criteria for finite element convergence is that the solution that we have has to be is piecewise continuous. That means, if I have one element here omega e and then another element, adjacent element omega e plus 1, then whatever approximation I have over element E, that is independent of the approximation over element E plus 1, but they share these common nodes, and the variation of the primary variable along this boundary should be same. So, when I approach this boundary of defined by nodes 1 and 3, I should get the same variation of primary variable whether I approach this boundary from omega e or whether I approach this boundary from e plus 1, element e plus 1, right. I should get the same variation, so that the solution is not discontinuous. They may be not smooth, but the function value primary variable should agree, exactly agree on this inter element boundary. So, C 0 continuity across the element boundaries. So, does our approximation satisfy that criteria, and how to judge that? I say that whatever we have done, our approximation u as a function of x and y given as interpolation n 1 u 1 plus n 2 u 2 plus n 3 u 3 satisfies this criteria. Now, on what basis do I do that? Do I claim that? First thing is, we need to appreciate that this is a first degree polynomial, right. So, let me just say a 0 plus a 1 x plus a 2 y. So, it is a first degree polynomial, and when I evaluate this, so when I evaluate this along this line, so let us just say for convenience I had modeled it as the along the y axis itself, and I intentionally did that because in that case I have a very simple example, simple case of x value, x coordinate being 0. So, this line connecting node 1 and 3, it is defined by x is equal to 0. So, the variation along variation of u hat e along node 1 3 is given by substitute x is equal to 0 here. So, a 0 plus a 2 y, y can change, y has a variation, right, it goes from 0 to some value here, right. So, y can change, but x value is uniformly 0. So, this is the constant, this is the variation of primary variable u along 1 3, right, and this is in element E. Similar variation I will have, maybe I can define these coefficients also as coming from element E corresponding to element E, right. So, now how many points do I need? I mean, I have u defined at node 1 and u defined at node 3. So, the variation of u along node 1 and 3 along the line defined by nodes 1 and 3, this is defined by the value of u at node 1 and value of u at node 3, right. So, this value of u at node 1 and value of u at node 3. So, these two values of u define the variation, and what is the variation that I can have? Polynomial variation with two values, two distinct values, it is first degree, is not it. So, it is the first degree polynomial irrespective whether I come from element E or whether I come from element E plus 1. And if I know two values and these primary variables, I mean these nodes are shared by the two adjacent elements. So, there is no way there can be different first degree polynomials on this common boundary between these two elements, as long as the primary variables, the nodes are being shared by the two elements. So, if the nodes are being shared by two elements, then the variation along this inter element boundary is also going to be unique, and therefore, the continuity of the function variable basic primary variable is guaranteed, is ensured across the inter element boundaries, right. So, that is what maintains the solution. So, what we say the finite element solution, instead of approximating constructing one approximation over the whole domain, we look at piecewise continuous approximation. So, U is continuous over element E, and then we construct another approximation for U over element E plus 1, and similarly for other elements, right, covering the domain. So, together they would be continuous across the inter element boundaries, and they would look like piecewise continuous. Within the element they will have smooth derivative condition, also constant derivative in this case, but across element boundaries the function value will be continuous, function value will be continuity of the function value will be guaranteed across the inter element boundaries, and so we will have the approximation piecewise continuous over the entire domain as we move from one element to second element, third element, and so on, and cover the entire domain. And we will discuss the next topic of higher order elements and the other method of constructing interpolation function in our next lecture. Thank you.